Just the horse fence. Cheap. Well, it's kind of weird. So I already have a chain link fence around two sides of the backyard and then a wooden fence on one side of it. But then my shop is in like the back corner of my yard. So I put a new fence, a horse fence, like coming off the shop and into the corner of my house so that I can drive around the shop without taking the gate down.
Makes sense.
So the dogs only get half the yard now.
Let's start. So we are going to go to the next chapter, which is chapter 4. I don't like so much this chapter.
We're already on 4. We're almost done.
Yeah.
It's weird. Summer classes always kind of trip me out.
Sprint, man.
It's crazy.
Mhm.
Is this the hardest chapter?
It has a lot of theorems, which I will just go slowly. Has some few theorems here and there. So this chapter is more of vector spaces and subspaces. So we'll do the 30 minutes of class and then 30 minutes of the review for the exam. Then you can go home and even 20 minutes for the review is okay. Okay, so we will start with number 1, and this one is the vector spaces. So we have actually dealt with this because vector spaces, the examples of the vector spaces are the real numbers to n, and then also a matrix, which is an m by n matrix. Those are the vector spaces that we dealt with previously. Okay, so let's define what is vector space is. So a definition, a vector space is a non-empty set, which we can name as the capital V, on which there are 2 operations. And these operations are addition, and actually scalar multiplication. And scalar multiplication. For the addition, then we can have 2 vectors, let's say u plus v, And this U plus V is actually an element of the whole vector space. And then also for the scalar multiplication, then C U is also an element of vector space where C is actually an element of real number. C is an element of real number. So there are 8 axioms which satisfies the vector space. So we can say subject to the following axioms. So we have 8 axioms that satisfies a vector space. So number 1, which we have dealt with actually during the vector space of Rn, and also for the matrix, which is the commutativity. So if you have U plus V, then this U plus V can also commute V plus U, where U and V are elements of the whole vector space. So that is the first axiom. Number 2, if we have U plus V plus W, then this is also equals to U plus V plus W, whereby you can add U and V, and then you add the W, or you can add V and W. They are equal. So for U, V, and W, elements of the whole vector space. Number 3, we're gonna have an element if there is an element, zero vector, which we still remember that is a zero vector in V, in the whole vector space V, such that U plus 0 vector, U plus 0 vector is equals to U. U plus 0 vector is equals to U, where U is an element of V, and also 0 vector is also an element of V. Number 4, for U element of V, there is an element V for U element of the capital V, U element, there is a small v there, which is also a vector. This is called a negative vector of U, the negative vector of U, where U plus V is equals to what? Zero vector. U plus V is equals to 0 vector. Number 5, C U plus V equals to, when you distribute this, the scalar here, then Cu plus Cv, where C is an element of real number and U and V are elements of the whole vector space. Number 6, C plus D and U, we can distribute a vector there where we get Cu plus Du, where C and D are elements of real number and U is an element of the whole vector space. Number 7, CDU is the same as CD and then U, where CD is an element of real number and U is an element of vector space. And then finally, number 8, if we have the identity 1 and U, this is the same as U for any U element of V. So those are the main axioms that should be satisfied for this to be a vector space. So those are the main axioms. So example of this, example number 1. A, the real number Rn is a vector space under the vector addition and multiplication of a vector of Rn by a real scalar. And we already saw this one. We already saw this previously. Another one is number B, an M by N, which is a matrix M by N, the set of all M by N matrices with real entries is a vector space under matrix addition and also scalar multiplication. We also saw this. We also saw this one. So this kind of, those are the main examples of vector space. Okay. If you will continue with mathematics, there's some other things that maybe you need to remember or you need to learn. And we'll see this one as a remark. Number 1, every vector space V has a unique 0 vector. Every vector space V has a unique 0 vector. This one might not be a textbook. Specifically, I just lifted this one from some of the notes. So we can prove this by, now suppose 0, 1, which is a 0 vector, and 0, 2 are 0 vectors in V. Then U plus 0, 1 is actually the same as 1. And also U plus 0, 2 is also the same as 1. It's also the same as. Then in this case, for any U element of actually V, then 0, 1 is basically the same as 0, 1 plus what? 0, 2. So that's 0, 1 plus 0, 2. And this is the same as it can commute. This is the same as 0, 2 plus 0, 1. And this is the same as what? 0, 2. 0, 2. So it shows that the 0 vector is unique. Another one, which is always very common, is every vector u of v has a unique negative vector, which we denote as negative u, which we denote as negative. So it also have a unique 0 vector, which we denote as negative u. Then to prove this, then suppose that v1, which is a vector, and v2, which is also a vector, are negative 0 negative vectors. So suppose v1 and v2 are negative vectors, then u plus v1 is equals to what? 0, right? Is equals to 0 vector. And also u plus v2 is also equals to what? 0 vector. 0 vector. Then in this case, then v1 is the same as v1 plus what? 0 vector, right? v1 is equals to v1 plus 0 vector. Then this 0 vector here can also be equals to what? This. So this can also be equals to v1 plus u plus v2, right? This 0 vector here can be the same as u plus v2 like that. And this can also be equals to v1 plus u, right? Plus what? v2 plus v2. And this can also commute. So this can commute. This can be equals to v2 plus v1 plus u, right? And this inside here can also commute. This is equals to v2 plus u plus v1. And this one is what? Is this, which is what? This is equals to v2 plus 0 vector. And therefore, this is equals to what? v2. So v1 is equals to v2. So it shows that it is what? This unique. Shows this unique. It's crazy, right? These are what we do in pure mathematics. Prove something and then you look at it and you're like, what nonsense are you doing here? Yeah. Another one, number 3. If u plus v is equals to u plus w, if u plus v is equals to u plus w, then v is equals to w. Then v is equals to w. This is what we call the cancellation law. The cancellation law. The cancellation law. So basically, you use the axioms that we just learned. So to prove this one privily, then prove. So we can say And note that minus u plus u is equals to u plus minus u is equals to 0 vector. It's equals to 0 vector. Then minus u plus v here is the same as minus u plus w. So if we introduce minus u in both sides at the left, so left cancellation, then this is basically the same as minus u plus v, and this is the same as minus u plus w, and basically these are equals to 0 plus v, which is equals to 0 plus w. 0 plus w. So then v is equals to w is equals to w. So that is the left. So we can do it at the right as well. So on the right, we just put this negative right here. So actually, get this here. So it's commuting. So it commutes. So it is the same thing. In this case, then it means that v plus 0 vector is equals to w plus 0 vector, which is the same as 0 v plus 1 equals to w. V equals to w. So you do it in both sides. Okay. Any question up to that? Another thing which you need to know here is this another theorem here, 1.2, whereby in a vector space V, we have 0 plus 0 multiplied by u is the same as 0 vector, and also c multiplied by 0 vector is the same as 0 vector, and minus u equals to minus 1 u for u element of v and c element of real number. So these are basic things that you need to remember. So the proof is just very simple. So you just prove using the axioms. So if you prove the first one there, then so we can prove this. So number one, there, this 0 u equals to 0 vector. Then 0 plus 0 u is still the same as 0 u. 0 plus 0 u is still the same as 0 u. Then also, when you distribute u here, 0 u plus 0 u is equals to 0 u there. Okay. This 0 u here is the same as 0 u plus 0 vector is the same as 0 vector there. Then 0 u is equals to 0 vector. Same thing with the second one. So let's see the last one here, number 3. Minus u equals to minus 1. Then to prove this, then we can just say, we can just use the first one here, whereby 0 u equals to 0 vector. 0 u equals to 0 vector. Then in this case, then 1 plus minus 1 u is equals to what? 0 vector. Is equals to 0 vector. So when you distribute u inside here, then you get to 1 multiplied by u plus minus 1 multiplied by u is equals to what? 0, 0 vector. So therefore, u plus minus 1 u is equals to what? 0 vector. So you can just take this to the other side, or you can bring it to this side. Then minus u is equals to what? Minus 1 u is equals to minus 1. And that is how to prove. All right. Example number 2. Example number 2, which is always very common. The first one is, if we let D be a non-empty subset of real number, the vector space V of all real valued functions of D is a vector space under the addition, which we can write this one as f plus g of x, and this is the same as f of x plus g of x, where for x element of D and f and g are elements of vector space. And for the scalar multiplication, then CF of x is the same as C of x for x element of D, C element of real number, and F element of the vector space. So, you need to show that this is basically the vector space. So to show this, then this should satisfy the 8 axioms. So they should satisfy the 8 actions. So first of all, the first thing you need to prove is you need to prove the non-emptiness. The non-emptiness. I'll just show you one of the steps, and then the others will just be similar to the axioms that we have just looked at. So the first thing you need to prove is you need to show that this is actually non-empty. So to check this one is non-empty, then we can write the 0 to be actually from D to real number. 0 from D to real number. Then for the 0 vector or 0 function, whereby i.e. 0x is equals to 0. 0x is equals to 0, where x is an element of D. So x is in D. So 0x will give you a number which is 0. And this 0 is actually an element of what? Of a real number. So this 0 is in R. Since 0 is in V, then V is non-empty. Since this 0 is in V, then it means it is non-empty. So therefore, it shows that V is actually non-empty. Shows that it is non-empty. Then after that, then you now start proving using those axioms. So the first one is commutativity. So F plus G of X is the same as F of X plus G of X. And also, this is similar to F G plus X plus F of X is the same as what? G of X plus F of X. So it shows that it commutes. So it commutes. So then F plus G of X is actually similar to G plus F of what? X. So it shows that it commutes. The second one is just the same thing. The second one is associativity, whereby you can introduce another one, F plus G plus H. All these of what? Of X. Then you can add this first, okay? So it is similar to just F of X plus G of X, adding the two of them there. And then later on you add H of what? X. So it is similar to adding G and H, and then you add F of X. So I don't want to prove this, it is very long because you need to prove all the 8 axioms there. So you can check it somewhere or anywhere else. So basically at the end of it, then it shows that this will satisfy the 8 axioms. And if it satisfies the 8 axioms, then it means it is a what? It is a vector space. It is a vector space. Okay. So when we meet, then we'll actually start from 1.3. This is basically the polynomials. The polynomials. So we will introduce what a polynomial is. I think you still remember what a polynomial is. So let's just introduce, and then when we meet, we will continue. So a polynomial, which we can name as a small p, is of the form. So this is of the form p of x, and this is equals to an xn plus an minus 1 xn minus 1 plus, you can continue like that, plus a1x plus a1 plus a naught plus a naught. So that is a polynomial where the scalars a naughts all the way to an are called the what? Coefficients. And our x is an indeterminate. Our x is indeterminate. Our x is indeterminate. So the other thing you need to know is the degree of polynomial. The degree of polynomial. The degree is actually the highest power of the polynomial. So the highest power here is what? N, right? The highest power is N. Then the degree of the polynomial is basically equals to N if AN is not equals to what? If AN is not equals to 0. And it is minus infinity if P is equals to 0. If this P is equals to 0 there, then the degree of that polynomial is there. Okay, so we will continue from there on Thursday. So let's see. This exam might also be so simple. Or you go to us. So let's just go through this. So you can determine whether the following is linearly independent or linearly dependent. So we remember the properties, right? So if there was 0 vector here, then it could have just been what? Linearly dependent, linearly dependent. But since there is no 0 vector, that you can go to the next steps. If there are more than 2, if there are more than 2, if n is greater or equals to 2, then you now look at the other properties. So one of them is you look at it if it is one of them is a linear combination of the others, or you can reduce it. And if you have the pivot position in each one of them, or if you don't have the free variable there, then they are what? Linearly dependent. So in our case here, so what you need to do is, for this case, then we can basically do what? Reduce it. So you write it in a matrix form of the form 1, 3, 1, minus 4, minus 9, 2, and then 0, minus 3, and minus 6. And then you reduce it. So once you reduce it and there is no pivot position here, then again, you need to remember that this linear independent and linear dependency is actually an example of what? Homogeneous. So you need to put 0, 0, 0 at the end. So once you find that this has all the pivot positions in each of these, then it shows that it has trivial solutions only. So if there is a free variable, then it means it is what? Linearly dependent. So if there is a free variable, then later on you come and do what? Look for the what? Linear relation. And what you get there is the linear relation. Any question? Any question on that? Okay, determine whether the column vector of the following matrix are linearly independent or not. So what do you do there? You introduce the what? The B1. You can introduce the B1, B2, and Bn because we are checking the columns there. Or you can just put zeros there. You can just put zeros. You can just put zeros. As long as, so what you want to see here is you want to see if there is a what? basic variable or free variable. So if there is a basic variable, if all of them are basic variables, then it is linearly independent.
Do we even need to do that since each column already has a pivot position?
You don't actually have to do it. You do what?
Just switch
You
to
just,
variable.
yeah, you just transpose it. So you just transpose it. And that is how it should be. Okay, number 3. Find the possible values of H such that the following vectors are linearly dependent. Did I give you something like this in your exam? I don't.
It's something similar. We did have to pick out variables, but I don't know if it was.
Oh, it was about, I remember, it was actually about,
Like whether there was one, none, or.
Yeah.
Many solutions.
Which would go hand in hand with linear independence and dependence though too, so.
Yeah.
Kind of did it.
Yep. So here it is actually what you need to do is for this one to give you a linearly independent or dependent, then you need to reduce this up to the point whereby it should not give you a what? 1, 2, 3, 1, 2, 3. So linearly dependent. So you write this one in 1, 3, 2, and then 2, 5, H, and then 0, -1, 6, right? So yeah, you can put 0, 0 there, okay? So what you want to look for is, you don't want to find a situation whereby, so you want to check whether this will actually have an entry here, a value here. So what value of H will it give you for it to be linearly dependent? So the value of H for it to be linearly dependent should be any value which will make this to be what? 0. So it should actually be giving you pivot position here. So actually it should be a free variable. Here should be give you a free variable. In this case, what am I? Here should give you a 0 here. So when you reduce it to a point whereby you find any value of H here whereby it's giving you 0, then that value there would be for it to be independent. So you need to look for the value of H which will make that one to be linearly dependent. Any question? Okay, number 4, determine by inspection whether the following are linearly independent, linearly dependent, justify your answer. Just by looking at them. Number D is already linearly what? Dependent. Just by looking at it. And then number 1. So if you look at number A, there are 1, 2, 3, 4. There are 4, right? The columns are 4. So P here and N here are 1, 2, 3. So P is greater than N. So if P is greater than N, then it is what? Linearly dependent. So it is linearly dependent. And the others you can actually check whether linear combination or something like that. All right, number 5, let that one be a linear transformation defined by T of X equals to A of X for X element of real number. So A is that and B is that. So what is, and the vector X element of whose image under T is B. So what do you do there? So what do you do over there? So find the vector x. So actually, what you need to do here is we are actually looking for what? Ax equals to what? Equals to b. So we are actually looking for the solutions of x. We're basically looking for the solutions of x. So to get the solutions of x, then you just reduce it completely. Just reduce it completely. Okay. Find the vectors x element whose image under T is a 0 vector. So in that case, then this B, so it is actually AX equals to what? 0. AX equals to 0. So you just look for the solution. AX equals to 0. Okay, number 6. Determine whether that one is a linear transformation or not. Justify your answer. So you check whether it is a linear transformation or not. You still remember how we were doing this? So you can basically write that one as a matrix form, whereby the coefficient here of x1 is 1. The next one for x2 here is what? -1, and then x3 is what? 1. When it comes to the next one here, it is 1, and then 2, and then what? Then 3, then 3. So for that to be a linear transformation, then you can let x1, x2, and x3 to be what? Zeros. If it is giving you 0, then basically it is a what? A linear transformation. It is a linear transformation. What about the next one? The next one is not giving you 0 because there is a -2 there, right? If you let x1, x2, and x3 to be zeros, then there is a -2 and 3 here. So it is not equals to what? 0, 0. It is not equals to 0, 0. Number 7, we've done that. You have that one in your examples. Number 8, we did this one in, I think 3.1. This is in 3.1, and we already did that. Find the standard matrix. What is a standard matrix? Just bringing those one. The E1, E2, and E3. So then together, that is a standard matrix. So actually, the standard matrix is basically of this form: TE1, TE2, and what? TE3. So that is a standard matrix. It's a standard matrix. And then find an x, which is an element of such that T of x equals to B, where B is that. So find x. So actually you're looking for what? The solution of x. The solution of x. So you just reduce it. You just reduce it completely. Then you get the solution of x. Number 9. Number 9, we did an example which is similar to that in section 2. Is it 2.9? Yeah, actually in section 2.9 we have a similar example like this. So go look at that. So how can you get the values of the image, which is you? How can you get the image of you? So in this case, you're actually looking for T of E1, and this is the same as Y1. T of E2, and this is the same as what? Y2. Y2 equals to Y2. So you substitute there. Substitution. Number 10, let that one be given by that. Similar thing to number 9 and also number 8. It do the same thing. Number 11, show that T is a linear transformation. Same thing to number 6. So you do the same thing to number 6. And then number 12, there are A, B, C. This is just addition and multiplication of matrices. We already did that, which is not difficult. A transpose, doing all those stuff, which is not very hard. And then number 13, if you let U to be that and V to be that, be a vectors in Rn, find U transpose V and U V transpose. So what is that? So U transpose. So if you have or U there is basically this U, our U here is the same as 1 minus 2 and 3. U transpose will be what? 1. It is not a comma. It is actually 1, negative 2, and 1, and 3. That is U transpose. Same thing to V. V, if you remember, make sure you note this one. When I put it like this, U equals to 1 minus 2 and 3. When you use this, what do you call these brackets? Parentheses, right? Then this is just similar to 1, negative 2, and 3. Okay, that is similar to that. Now, our U transpose in this case is you put these brackets now, 1, negative 2, and 3 there. 1, negative 2, and 3. And then you multiply them. Okay, number 14, find the inverse. That is so simple. You still remember that. Use the inverse of the coefficient to solve the linear system. Use the inverse. So in this case, to get X is the same as A inverse and what? And B. A inverse B. A inverse B. So do not use, if I ask you to use the inverse of the coefficient, do not use the Cramer's rule. So unless we specify to use the Cramer's rule, and Cramer's rule will not come, will not be there in your exam. Okay, number 16. It's also similar to what we've just done previously. So you just write those coefficients there. You write find A inverse, and then you do all those stuff there. Number 17, you will find it in your exam. This will be in your exam. Find the inverse of the matrix using, you remember where you are adding the columns here. Yeah. Finally, number 18, determine whether each of the following matrix is invertible, singular, or that. So for it to be invertible, then the determinant should be what? Should not be equals to 0. Okay. If you have any questions, I'm always available. You can email me. All right, I will see you guys tomorrow during your exam.
So excited.
Yeah.
Well, I like math, but I hate math tests for some reason.
Yeah.
They always make me nervous for some reason.